10:20. Why don't we go ahead and begin here? First off, administrative announcements. I guess this is quiz 3 here maybe is the first counterexample that we have to the general rule. Remember at the beginning of the semester, I said that typically the quizzes go through the Monday before the quiz, right? Doesn't include the Wednesday stuff because there's not a lot of time, a lot of turnaround for you to really study that and whatnot. So the counterexample here would be that the Monday stuff from this week, 14.6, gradient and whatnot, is not covered on quiz 3. It'll be covered on quiz 4 instead. And this is just because there's enough topics on quiz 3 as is, right? So we have 14.1 and 14.3. So all of the domains, ranges, level curves, partial derivatives. Then 14.4 is the linearization and differential stuff. 14.5 is the chain rule. And we also had a 16.6 intro when we were talking about parameterizations of surfaces, right? So we already have enough topics. We don't need 14.6 as well. I think quiz 4 will have like 14.6, 14.7, maybe 14.8 or something like this. So it'll have maybe 3 with those, and we already have 5 on quiz 3. So anyway, the quiz tomorrow does not cover Monday stuff about the gradient vector. Of course, right, still partial derivatives are fair game. That was 14.3, but you won't need to put them in the vector form and find a max rate of change or stuff like that. Not yet. I think that's my only administrative thing. Any questions before we jump into the math for today? How's everyone feeling? Yeah. Okay. So yeah, today we're talking about mins and maxes. In the pre-class video, I wanted to recall or remind you about, when we did this in Calculus 1, what did it look like? Because we will be extending this, of course, to here in Calculus 3, the multivariable case. So starting off with definitions for local mins and local maxes. And that is that it's the smallest thing in some neighborhood, around the set of points, the smallest value. And of course, if these inequalities hold true for all points in the domain, then it would be the absolute mins and absolute maxes. If you wanted to find a min or a max in Calculus 1, you became very interested in critical points. Critical points housed all of your potential mins and maxes. There were also boring critical points. So it's not the case that every single critical point out there was necessarily a min or a max. But the critical points in Calculus 1 were just when your derivative was equal to 0. Nowadays in Calculus 3, we have several options for derivatives, right? We could have a derivative with respect to x or a derivative with respect to y. And in our case, we need both to be true in order for there to potentially be a min or a max there. So we have an and statement. We need the partial derivative with respect to x and the partial derivative with respect to y to both be 0. By the way, in some textbooks out there, just as a heads up, I have seen this written as your gradient is equal to the 0 vector, right? Just because the gradient, well, the first component would be your x partial derivative, and the second component would be your y partial derivative, right? You need both of them to be 0, so that would be the same thing as the gradient being the 0 vector, right? 0 for each component. So that is another way that you can write this if you wanted. All right, so you have a critical point there. We're going to be primarily dealing with when both are equal to 0, because that's when our test will work. Technically, if either one of these does not exist, sometimes wonky things can happen. Likewise in Calculus 1, right? Calculus 1, the classic example when a derivative does not exist is going to be at the absolute value of x. It has this interesting point when x is equal to 0, where you have this like jagged edge sort of deal. The derivative doesn't exist here. The left-hand limit is not equal to the right-hand limit. Again, technically derivatives are limits. And so it doesn't exist there, and yet we see there's a min. So again, our rules won't really work when you have one of these not existing. So we won't really care about that so much in our class. I think there is a project out there that deals with this a little bit more. But as far as homeworks, quizzes, and exams and whatnot, we're going to be primarily interested when both derivatives are 0. And then finally, critical points that are not a min or a max, so are neither one of these local extrema, are considered saddle points. So saddle points nowadays, I guess if we wanted to go back to Calculus 1 real fast, X cubed would be an example technically then of a saddle point. At 0, the derivative is 0. And yet it's not a min or a max, right? If you go a little bit to the right, you get bigger values. And if you go a little bit to the left, you get smaller values. So it's not a min or a max, and yet it is a critical point. So now with our Calc 3 terminology, we would call this a saddle point. Okay, so we know about critical points. The next thing is, how then, if we have critical points, do I find mins and maxes? And so in our Calculus 1 days, we had something called the first derivative test. And I think that this was everyone's favorite derivative test for classifying mins and maxes. And you had to go across your critical point and figure out if it went from increasing to decreasing or decreasing to increasing, right? How does this act? And when we think back to now, if we're in a multidimensional case, there are many ways that you could go across the point. And they may not all agree, which would be quite sad, right? If they don't agree, we'll end up having a saddle point. And so it's very hard to test all possible ways to go across a point. And so unfortunately, the first derivative test doesn't work for us here in a multivariable case. However, in Calculus 1, in most curriculums, right, we also bring up a second derivative test. And it turns out the second derivative test will work for us. We don't need to travel across the point for the second derivative test. We're just going to be testing the concavity at the point. And this will enable us to recover a test that'll help us classify mins and maxes. So as I alluded to here, we have multiple versions of a second derivative, right? We could do two derivatives with respect to x, two derivatives with respect to y, or we can do a mixing, right? One x, one y sort of deal. And unfortunately, you will need all of them in order to be able to classify. So the second derivative test will be a bit complicated. So that's where we ended for our pre-class video. Any questions about this before we jump into our new stuff for today? All right. So then here is our second derivative test for a two-variable function. You need to have a relatively nice function. That is the function itself, its partial derivatives, first order and second order partial derivatives, should be continuous on a disk centered at the point of interest. Then if you have a critical point, and it's one of these nice critical points where the derivative is 0 in both cases, not where it's undefined, then we're going to go ahead and calculate out this d thing. So this d at AB is the determinant of a matrix. That's why it gets this d value. And so it goes your two partial derivatives, both with respect to x at our point of interest, our two derivatives, both with respect to y at our point of interest, minus the mixed partial derivatives, 1x, 1y, at our point of interest, AB, quantity squared. So the matrix that this is I think in 14.3 you got a problem about this. It is the Hessian matrix. It takes all of your second order partial derivatives. And you can notice here that at least when I wrote it in the matrix form, you know, I did keep the ordering of our derivatives. So we're taking x derivatives in the first row first, and then y derivatives in the second row first. So we have f sub xy and f sub yx. However, when I went and I wrote it over here, the simplified version, right, I just wrote f sub xy squared. So this is using Clairaut's theorem. So Clairaut's theorem requires us to have nice second order partial derivatives and whatnot. So that's where we're using part of that there, that you can take derivatives in either order. So either x first, then y, or y first, then x, and they will give the same value. So that's a bit of simplification going on there. Okay, so you have this d thing, right? And like I said, this is where we need to use all of our second order partial derivatives. Once you have d, if d is greater than 0, what I want you to think about is that we are in Calculus 1 world. So Calculus 1 world, now once we know we're in Calculus 1 world, the second derivative test is the exact same as the second derivative test in calculus 1. That is, if your second derivative, both with respect to x, is less than 0, then you're going to have a local max. So I know it's a bit strange, right? But your second derivative, right? When you see a negative, you think, well, maybe that's a min, right? It's a small value. Maybe that should be a minimum, right? But remember, the second derivative test is telling you something about concavity. So this is saying that you're concave down. So when you're concave down, it's bending downward, and you can kind of see that max. So that's why it's a local max there. Again, kind of a review from calculus 1 days. If your second derivative is greater than 0, then again, you're concave up. That means you're going to have a local minimum. So it's a bit strange though, right? Because you see a bigger value there. You would think maybe that's a maximum, but no, it's the opposite because it has to do with concavity. If your determinant, your d value, is less than 0, I'd like you to think that we're in Calc 3 world, right? And the new thing from Calculus 3 is saddle points. So we now have something called a saddle point. And notice you don't need any additional tests here. Just once that's less than 0, that's it. You have a saddle point. And then finally, the most annoying thing about the second derivative test is that it doesn't know everything. And that is, there is the possibility, if that d is equal to 0, that the second derivative test doesn't know what you have there. That is, it's not to say that it's a saddle point, and it's not to say that it's necessarily a min or a max. It could be any one of these things. It doesn't know. And so you would need to do more sophisticated tests, not really covered by our class here, in order to figure out if it's going to be a min or a max or what's going on there. So this does have limitations, and those limitations show up when your determinant is equal to 0. All right, I see there was a question in the chat. Let me look at this really quick. And then also any questions here as well. In this course, are we going to assume that f sub yx and f sub xy will always equal to each other? Again, there could be some projects, or I guess even technically a tricky true-false thing or whatnot that, you know, it's true that these things don't have to equal each other. But yes, I mean, 99% of the time in our class, they will be equal, especially when the conditions like this are given to us, right? Again, for Clairaut's theorem to hold true, you need to have continuous partial derivatives, and then you can do that flipping. So especially when the theorem starts off with, hey, this is part of our hypothesis, then yes, we don't even need any additional assumptions. It is true. Yep. Good. Any other questions here? Yes, here in the middle. What would d equaling 0 look like on a graph? No, so if d equals 0 on a graph, it could look like either a min or a max or a saddle point. It may not look like anything special whatsoever. Usually this would have to do with higher degree polynomials, for instance, is the easiest way to achieve this. So it's probably more likely to level out there. Good question. I have a question for you guys. Why is x special? Why is it the x derivative is less than 0, the x derivative is greater than 0? Why not y? What's wrong with y? Nothing's wrong with y. Yeah? Hmm. Well, again, so we're in three-dimensional space. So x just runs like this, and y just runs like this. I mean, I can, you know, if you're looking at the x-axis here, you can very easily look at kind of a very similar thing, you know, by just turning my head slightly. So the answer is you can make this same ruling with y's, that actually y is equally good as x. And so we'll see in all of our examples, it turns out if the second partial derivative with respect to x is less than 0, then it'll also be true that your second partial with respect to y is less than 0. Just kind of, it aligns nicely with calculus 1. Back in calculus 1, we only had x's, so But this theorem works perfectly fine if you use y's there instead. All right, so in 12.6, this hyperbolic paraboloid, I said it looks like a saddle. And it would be nice to show then, right, that there really is a saddle point there. I think I may have even said that. So here is our hyperbolic paraboloid, z equals y squared minus x squared. It does indeed have a saddle point. So I'm going to try to show that now with my algebra, right, or really with the equations, right? We're not going to graph it so much. We're going to use our equations, our calculus, and our algebra in order to classify and, of course, find our critical points. So starting off here, in order to find, and really these are quite often two-part problems, right? The part A really could be find all of your critical points. Part B could be classify all of your critical points. So the finding of the critical points. Well, remember, I'm going to be taking some partial derivatives, and I'm hopefully finding when those are both equal to 0. So if I take my partial derivatives here with respect to x, I get negative 2x, and with respect to y, I get 2y. So first of all, you can get critical points any place where these are, either one of them is undefined. Is there any way to make these undefined? Well, no, you're not doing any of the things that would break your equations, for instance, division by 0, or taking negative square roots, or plugging 0 or negative into a logarithm, right? No matter what x and y are, when you plug them in, it will make perfectly fine sense. So there's no way to make either of these undefined. So my only hope for critical points are to solve the equation when your x partial derivative is equal to 0 and your y partial derivative is equal to 0. Of course, if you need both of these things to be true, the first one is equivalent to x must be 0. The second one is equivalent to y must be 0. And so again, if you need both of these to be true, that means that there's only one point that satisfies both your x and your y partial derivative are both 0, and that's when x is equal to 0 and y is equal to 0, right? You're at the point 0, 0. So this is my only critical point. Now we can move on to, now that we've found all of our critical points, can we classify these things? So classifying our critical points, this is what we need to use our second derivative test for. Which, by the way, so this is a lot of information here. This is largely captured on our formula sheet. So again, you should look at your formula sheets, know what's on there and what's not on there, especially when it comes to quizzes and exams and all that sort of stuff. So you'll see that largely this is on the formula sheet. So you can reference that. You don't have to memorize it completely. All right, classifying. Classifying largely deals with these second partial derivatives. So I'm going to go ahead and spend a little bit of time and first just kind of calculating out some components. So I need to take two partial derivatives with respect to x. Well, I already have one up here. I could do another one, and that's just going to be negative 2 times 1 then, right? Because the derivative of the x would be 1. If I did a mixed partial, one with respect to x, then one with respect to y, well, the derivative of negative 2x with respect to y is going to be 0, right? There's no y's. Or likewise, if I had decided to switch that up and I did y first and then x, again, you would get 0. Mixed partials are going to be equal here. And then finally, if you take two partial derivatives, both with respect to y, you're going to get 2. So with this, we can now calculate out our d. So this would be d technically at 0, 0. Notice that these are such, this is a simple enough equation that when we took two partial derivatives, all of our variables went away. That won't necessarily happen, but here we don't have any place to plug in our point 0, 0. If we had x's and y's left over in our partial derivatives, we would have a place to plug in 0 for x and 0 for y. We'll see examples of that in our next problem. All right, so our determinant, right? This is going to be our matrix here, negative 2, 0, 0, 2, right? Or again, you can just use the simplified version, whatever you would like. And so this is going to be equal to negative 4 minus 0. That's going to be equal to negative 4. That is less than 0. So that means I'm in calculus 3 world. The new thing from calculus 3 is a saddle point. So by the second derivative test, 0, 0 is a saddle point. So again, I claimed back in 12.6 that this hyperbolic paraboloid looked like a saddle. It has this kind of saddle point thing. And you know, if you looked at the parabolas going in the two different directions, right, you have one that kind of stretches down and one that kind of stretches up. And this point here is this saddle point. This point here, when in one direction, if you're looking, it looks like a max. At one direction, if you're looking, it looks like a min, right? That point there is going to be that saddle point. So there's our hyperbolic paraboloid and kind of what these saddle points look like. They kind of have this conflicting information here. My best attempt at the saddle. All right, questions? This was a relatively nice setup. Let's make it a bit more difficult on ourselves. So same sort of deal, find and identify all of your mins, maxes, and saddle points. So this would be equivalent to say just find and classify your critical points. And now we have our function with some cubics. So same sort of deal as before when I'm finding, right? This largely has to do with taking our first order partial derivatives. And so when I take a partial derivative with respect to x, I'm going to get 3x squared plus 3y plus 0. And if I take a partial derivative with respect to y, I'm going to get 3x plus 3y squared. In order to have critical points, you need to be able to make one of these undefined or get both of them to be 0. So just as before, there's no way that I can make either one of these undefined. I would need to be able to divide by 0 somehow. I'd need to be able to take a negative square root or square root of a negative. Or I need to be able to plug in 0 or negative into a log or something like this. But this is just polynomials, right? No matter what x and y I plug in, there's no way that this is going to give you anything but real numbers. So you can't make these undefined. So the only way that we can get critical points is if both your x partial derivative is equal to 0 and your y partial derivative is equal to 0. So now you can see that in general, right, we have a system of equations to solve here. I need to know when both of these things are true. And sadly, this isn't even just like a linear system of equations, right? Because it has x squareds in it. So we need to be pretty good at solving system of equations, which is an old algebra skill, right? Well, one way that we can do this, for instance, if I was going to start working on this, is that I could divide by 3, and I could rearrange and I could solve y equals. So in this case, maybe I'd have y is equal to negative x squared. So again, dividing by 3, that would give me x squared plus y equals 0, and then I could move the x squared to the other side. For this one here, well, solving y equals would be a little bit of a pain for my second equation because it'd have a square root, right? And whenever you have a square root, you would need a plus and a minus. So, well, we've gotten a little bit better in our class solving for x and kind of sketching what those would look like. So maybe let's instead go ahead and I'm going to do the same sort of deal, but now solving x equals. So I'm going to divide by 3, and then I'm going to subtract the y squared over to the other side. And so I get x equals negative y squared. So I want both of these equations to be true. One thing that's sometimes useful, this problem, maybe it's not needed so much, but it's not a bad idea to kind of think about this graphically a little bit, right? If I want both of these things to be true, and if I was to graph these two, right, y equals negative x squared, so your x partial derivative is equal to 0 everywhere along this parabola. Y equals negative x squared. Your y partial derivative is equal to 0 everywhere along this parabola. And again, kind of, we practiced this a little bit back in 12.6, but if you need to use the point plotting method, please use the point plotting method. But this is, because it's x equals, it's going to open up left or right. And because we have negative y squared, that means that it's open up to the negative x values, opens to the left. So we can see that if you want the first equation to be true, you need to be on the red parabola. If you want the second equation to be true, you need to be on the purple parabola. If you want both of your equations to be equal to true, well, then you're interested in when these things intersect. So now at very least, we can see that there are two solutions. One of them, I could make a strong argument, is at 0, 0. But still, right, there's algebra associated with solving a system of equations. So we can see that maybe this second one here has a negative x value and a negative y value, but I didn't do a good job maybe with the scaling or anything like that. So let's figure out with the algebra, how could we solve for this? Well, maybe now that we have these things set, x equals and y equals, we could use a substitution method for solving our system of equations. So if I go ahead and I substitute in maybe my second equation into my first equation, I would have y equals negative x squared. And again, according to our second equation, x is equal to negative y squared. So this would be the same thing as y is equal to negative. And let's see, so if I take a negative and I square it, it becomes positive. And if I take y squared and I square it, it becomes y to the fourth. So at this point, right, I'm trying to solve this algebraic equation. Some folks, if they're going too fast at this point, they would just divide y on both sides, right? But remember, you can only do this if y is non-zero. If y is 0, then you've divided by 0, right? And that's actually ruined it because you've lost a solution, right? You wouldn't actually get this origin point. If you do divide by 0, you kind of lose that information when y is equal to 0. So a better way to go about solving such an equation is to rearrange as a polynomial and then factor and solve. So if I rearrange like this, y to the fourth plus y is equal to 0, then I can take out a GCF, greatest common factor. And remember, if two things multiply to give 0, one of the other has to be 0. So this says that either y is equal to 0 or 1 plus y cubed is equal to 0, which this can be rearranged. Y cubed is equal to negative 1. And thank goodness cube roots don't have any problems with negatives, right? You can plug in the cube root of negative 1 into your calculator and it'll just tell you, well, negative 1's the answer, right? If you take negative 1 and you cube it, you get negative 1. So either if y is equal to 0 or if y is equal to negative 1, this will satisfy. Now we need the x values. So we could plug these y values in up here into my x equals equation. And this would give us 0, 0. Of course, if I plug in y equals 0, I get x equals negative 0 squared. Okay, that's x equals 0. And then if I plugged in y equals negative 1 into there, well, negative 1 squared would be 1, but then there's that minus sign out in front. So that would be negative 1. So this would be negative 1 for x, negative 1 for y. So if I wanted a scaling, right, it'd be like that. You can see that solving or finding my critical points in this case was more difficult. Right? The last one, the system of equations, was very, very nice to us. I will tell you that, in this section here, you will need to solve system of equations a fair amount, at this level, maybe a tad more difficult. And we'll also be solving system of equations a lot in 14.8 when we talk about Lagrange multipliers. So I would recommend, if you are at all hesitant about solving system of equations, face your demons now and try to get better at it. Because if you try to hold your breath through it and you just try to survive until the next section, unfortunately, it's there too. And so it's better to kind of confront this and try to get better at solving system of equations now rather than later. Okay, so we've found all of my critical points in this case. Now we need to classify, right? So I want to identify them as mins, maxes, or saddles. So for this, we go to our second derivative test. Second derivative test, of course, has a lot of second derivatives. So I'm going to go ahead and calculate out here some second derivatives. Starting off with looking at my x derivative and taking another x derivative. So that's going to be what, 6x, I believe. If instead I looked at my x derivative and took a y derivative, I think I would just get 3. And then if I was to look at my y derivative and take another y derivative, I would get 6y. So now my determinant equation, which again, you can go ahead and set up as an actual determinant if you'd like. Or you can go ahead and just use the simplified version, right? We're going to have 36xy minus 9. So now you can see that we actually have a place to put in x values and y values. So it will depend on what critical point we're at. So for instance, when we are at the point 0, 0, we're going to have d of 0, 0 is equal to -9. Right? So once I plug in 0 for x and 0 for y, I get -9. That's going to be less than 0. So 0, 0 is yet again a saddle point. Now, on the other hand, if we were to plug in x equals -1 and y equals -1, right, we would have d of -1, -1 is going to be equal to 36 minus 9, which is equal to 27, which is greater than 0. So now we're in a case where we're in calculus 1 world. So we can look at f sub xx at -1, -1. So f sub xx is 6x. So that's just going to be 6 times -1 will be -6. This is less than 0, which means that we're concave down. When we're concave down, this is a local max. Notice also, if you wanted to use f sub yy, you would also get -6. And so you would still classify it as a local max. All right, so we have now found all of our critical points and classified all of our critical points. Any questions on this one here? All right. So then, I think I have another problem for us. I'd like to use the 14.7 method to find a shortest distance between a point and a plane. And so, I mean, I'm aware, 12.5, we have another way of finding a shortest distance between a point and a plane. The problem is, using the 12.5 method, if you were to use any other surface, right? Imagine instead of a plane, you wanted a cone or a hyperbolic paraboloid or an elliptical paraboloid, right? If you wanted to use any other surface, that method no longer works. However, with 14.7 method, you can do any of those 3 problems and much more. You can use any point and any surface, and you can find a min or a max to it, right? And so this 14.7 method is stronger and will be able to be used in more situations. In fact, there is a WebWork problem that asks you to find a shortest distance between a point and a cone. You can't use the 12.5 method on that, right? You need to use this method. And so that's why we're going over this. So at the end of the day, here are the keywords: shortest distance. These are the keywords that say that I want a minimum of a distance function. Don't really care about the maximum here, but we're caring about the minimum. And so this is where I need to start kind of think back. And maybe the first thing that I would do is I'd pull out my distance formula. back from 12.1, right? If I have a couple of points, we know how to find the distance between these things. And this will be our function that we're trying to minimize. Now, one of these points is fixed. It doesn't move, it doesn't do anything fancy, right? And that is this 1, 0, 2. So I'm going to go ahead and maybe say that this is, my x1, y1, z1, right, is going to be 1, 0, 2. My other point, well, I don't know where it is. It's somewhere on this plane. And so it could be, really anywhere on this plane. But the fact that it's on the plane does mean that z, for instance, needs to be equal to 4 minus x minus 2y. So if I solve that, z equals, right? A point in space could be literally any combinations of x's, y's, and z's. But if it's on the plane, this plane here, we know that whatever x and y is, the z can't be any random thing, right? It has to be on the plane. So once you've determined where your x and y is, it's got to be a specified height to hit that plane. So I'm going to go ahead and let my x2 just be equal to the variable x. Again, I don't know what it is yet. y2 is going to be equal to just y, a variable. But then z2 is going to be equal to, we want to make sure that it's on the plane. So, right, we could do this x2 minus y2 here. So that forces us to be on the plane. So let's go ahead and substitute some of these things in. So x2 is just x. X1 was 1 here. Y2 is just y. Y1 is 0. And then z2, well, we're going to go ahead and swap this out so that way we make sure that we're on our plane. So this is going to be our 4 minus x minus 2y minus z1 happens to be 2. So now instead of having a distance formula between any 2 points in space, I have a distance formula for a distance between my point 1, 0, 2, and I've made sure that we're on the plane. So the plane, again, has the equation z equals 4 minus x minus 2y. So that's where I guaranteed that we're on the plane. So I now have a distance equation between these two things. All right, notice that there are only x's and y's. And so using our strategy that we've come up with here in 14.7, I can find mins and maxes and classify those, right? We don't yet know how to do this if there was x's, y's, and z's. All of this stuff that we've been doing so far just has x's and y's in our equation. All right. Well, now is where, I don't know. So there's a straightforward method to doing this, and then there's a trick that saves some time. I think maybe because you do use this in other places, it'd be better to learn the trick that saves some time now rather than waiting till later. So I would like to bring up, so if, what's the best way to say this? Let's say the square root of f is minimized exactly where f is minimized. This will make a nice impromptu theorem here. So if you're interested in minimizing the square root of something, that is equivalent to minimizing what's inside of the square root. The proof for this is simply that the square root function, square root function is increasing. So that is, if I was to draw a quick picture of it, something like this. Notice that if you want to get the minimum value out, right, the output here, the y value, you're going to want to plug in something smaller, if you plug in something bigger, right, because it's increasing, you're going to get a bigger value out. So if you're interested in minimizing a square root, if you minimize what you plug into it, right, in this case, if maybe A is smaller than B, then your output, the Y values, are going to be smaller. What this enables me to do and why I care and why I'm bringing this up now is that I'm about to start taking derivatives. I'm not looking forward to taking the derivative of D at all. It's horrible looking, right? But it becomes much easier if I make an argument that I don't actually need to include that square root. And so this is saying if I can minimize what's inside of the square root, then I'll know that D is also minimized there. So I'm going to take F to be equal to what's inside of my square root here. I'm also simplifying just to two small things, right? Instead of y minus 0, oops, I forgot my plus sign. Sorry about that. Instead of y minus 0, I'm just writing y squared. And I saw there's a 4 minus 2 in that last term. So 4 minus 2 is 2. So I'm going to take f to be what's inside of my square root. I'm going to try to minimize that. And if I can minimize that, right, I'll know that my distance function, which is the square root of this, is minimized. All right. So we've done all the hard stuff. Now it's just kind of the same sort of stuff we've done in the previous two problems. So let's first go ahead and try to do, again, our goal is to find minimums. We know minimums are right going to be critical points. So maybe I should first try to find critical points, and then I'm going to classify and hopefully find a minimum. So, okay, taking a partial derivative with respect to x, I'm going to get 2x minus 1s plus 0 plus 2 minus x minus 2y times the derivative of the inside. The derivative of negative x is negative 1. Partial derivative with respect to y. I'm going to have 0 plus 2y plus, again, kind of bring this down, reduce my power by 1, multiply by the derivative of the inside. The derivative of negative 2y is negative 2. All right. Again, these are polynomials. There's no division. There's no square roots. There's no logarithms, right? There's no place to make this undefined. So my only hope is that both of these are equal to 0. So finding critical points is when both of these are equal to 0. So let's see if I can't simplify a little bit while I go here. So I distributed the 2. Now let's try to distribute a negative 2 to each piece. So that would be what? Negative 4 plus 2x plus 4y. So I would like that to be equal to 0. And so I'd have what? 2y here. And then I'm going to just try to distribute a negative 4 to each piece. So negative 4 times 2 would be negative 8. Negative 4 times negative x would be plus 4x. And negative 4 times negative 2y would be plus 8y. All right. So we want to know when both of these are true. Nice system of equations. Let's go ahead and try to simplify this a little bit more, and then maybe we can substitute in one to the other or something. So let's see. I have 2x and 2x, so this is going to be 4x. I also have plus 4y. And then I'm going to take my constant to the other side here. So I have negative 2 and negative 4. That would be negative 6. So on the other side, adding 6 to both sides. This is the real exciting part of class, right? Just simplifying equations, trying not to make mistakes. All right, next up we have 4x plus 10y. And if I bring that negative 8 to the other side, that's going to be equal to 8. So now I have all of my like terms combined. I have these looking relatively the same. And so, okay, well, this is where we need to solve this system of equations. Now it's looking a little bit cleaner. And so we could use a substitution method by all means. However, I see this 4x and this 4x, right? They're perfectly the same. And so I'm interested in linear combinations, maybe more in this case. So another strategy for solving a system of equations is sometimes you can add or subtract one equation to the other, right? And so I'm going to go ahead and subtract my second equation from my first. And my strategy, why I'm interested in this, is because now the 4x minus the 4x perfectly go away, right? And what I'm left with is going to be negative 6y is equal to negative 2. And this is very easy to solve for y. Right? So I now know that y is equal to 1/3. Once I know that y is equal to 1/3, I can plug this in into either one of my original equations here. And the beauty is it should give out the same x value, right? Because we're solving the system where they're both true. So you can choose either one. I'm going to go ahead and choose the first one. All right. So 6 is the same thing as what, 18/3? If I go ahead and subtract away 4/3, that's going to give me what, 14/3. And so x is going to be equal to 14/12. That's going to be the same thing as 7/6. Maybe paranoid really quick and just double check and make sure this is the same as when I did it before class. Yeah, that's the same thing as I got before. So I don't think I made any small mistakes, but please feel free to tell me otherwise. All right. So with all of this, we only have one critical point. Boy, I hope it's a minimum, huh? So we're looking at the point 7/6, 1/3. Let's go ahead and plug that in and hopefully find a minimum. So if we go ahead and start taking second partial derivatives. When I'm looking, right, I'm going to be looking right here, I suppose, for my f sub x. It's a little bit more simplified than the first thing that I wrote down, right? But I haven't started to rearrange or anything. So if I take a derivative, second derivative with respect to x, I get 2 plus 2. That's just going to be equal to 4. If I was to instead take a partial derivative with respect to y to get my mixed partials here, again, there's just a 4y here. So that's also going to be 4. And then finally, if I was to look at my y partial derivative and take another derivative with respect to y, let's see, that would be 10. So my d is going to be, let's see, 4 times 10 minus 4 squared. And you can write out the actual determinant if you'd like. So that's going to be 40 minus 16. The big thing is that that's positive, 24. And because if you look at either your x partial derivative or your y partial derivative, this is greater than 0 as well. That means it's concave up. And so this point, 7/6, 1/3, is a minimum. Now, I'm basically done. However, the question doesn't ask, where does the minimum occur? The question asks, find the shortest distance. So now I know where the minimum occurs, where that shortest distance is. But when I actually want to go and find the shortest distance, right? Well, now I need to go back and I need to plug it in into my distance formula. If you plug it into f, right, it won't quite give you the right answer. It'll give you the distance squared. So notice this theorem says the square root of f is minimized exactly where f is minimized. It's not saying that it'll give you the same number out, right? You're missing a square root, but the location is the same. So we have the location. Now it's just a matter of plugging this in. So my distance formula was the square root of an x minus 1 quantity squared plus y minus 0 quantity squared plus 2 minus x minus 2y quantity squared, all inside of my square root. So again, I'm going back up to my distance here. X minus 1, I know X is 7/6. Y minus 0, I know Y is 1/3 now. And again, I'm just plugging in 7/6 for X and 1/3 for Y. There's a 2Y there. That's what made us the 2/3 over here. And of course, I simplified that 4 minus 2 is still 2. So if you'd like to, you can plug this in exactly as is into WebWork or into your calculator to give you a decimal approximation, or you could take a line to simplify a little bit more if you'd like less to type. But the option's up to you. All right. 11:10 on the nose, a perfect class. Any questions? All right, we get another day of this stuff. We'll talk about absolute mins and absolute maxes in Friday's class. So this is not done yet. You will get more practice with it. This is difficult stuff. So I'll see you on Friday. I'll stick around if there are any one-on-one questions. Otherwise, good luck on your quiz tomorrow. And again, see you Friday.